All right, today we're going to tackle a force you feel every single second of your life, whether you realize it or not. Friction. I mean, it's the invisible force that stops your coffee cup from sliding right off the table. It's the reason you can even walk at all. But how does it really work?
So, let's kick things off with a question that I bet you've all felt. You're trying to move some heavy furniture, right? And that first push, man, it takes a ton of effort. But then, once it finally starts sliding, it suddenly gets easier. What's going on there? That feeling right there is the key to really understanding friction. Well, to get to the bottom of that, you gotta realize that friction isn't just one thing. Nope. It actually has two totally distinct personalities. And which one you get depends on one simple fact. Is the object moving or is it not? And what do we call them? Well, we call them static friction and kinetic friction. Just think of static friction as the grip force. It's kind of like a powerful glue that holds an object in place before it starts to move. Kinetic friction, on the other hand, is the slide force. It's that drag you feel once something is already in motion. Okay, so let's dive into this a bit more. Static friction is actually pretty clever. See, it's not some fixed number. As you start pushing on that box, it pushes back with the exact same force, keeping everything perfectly still. But it has a breaking point. There's a maximum limit it can take before that powerful grip finally gives way. The very instant you push hard enough to overcome that maximum static grip, the box starts to slide. And bam, a totally different, weaker force takes over. That's kinetic friction. And that's why it feels easier to keep the box moving. You've beaten that initial stickiness, and now you're just dealing with a much gentler sliding resistance. So here's the absolute key to all of this. The coefficient for static friction, that's just the number that tells us how grippy a surface is almost always higher than the one for kinetic friction. This chart, which is based on a problem from our source material, shows it perfectly. It takes more force to overcome that 0.5 static grip than it does to fight against the 0.4 sliding friction. All right, so now that we've got the basics down, let's see how things get interesting when we leave the flat ground behind. What happens when you put that same box on a ramp? Right, so when the ground isn't flat anymore, a whole new player jumps into the game. It's not just about you pushing against friction anymore. Now, gravity itself is actively trying to pull the object down the slope, and friction has a whole new battle on its hands. Let's actually use a problem from our source to see these forces in action. We've got a 6-kilogram block sitting on a pretty steep 60-degree incline. I mean, your gut tells you this thing wants to slide down, right? So let's break down the why. Okay, first things first, gravity. It's always pulling straight down, toward the center of the Earth. But the ramp is in the way. So the ramp pushes back with something physicists call the normal force. It always pushes perpendicular to the surface, and it's what's literally stopping the block from falling through the ramp. And this is where friction becomes the hero of the story. Because a part of gravity is pulling the block down the slope, static friction has to act in the exact opposite direction, uphill, to hold it in place. Right now, it is the only thing preventing this block from just sliding away. So, how strong is that frictional grip? Well, it all comes down to this one number, 0.6. That's our coefficient of static friction for this surface. The higher this number, the grippier the surface is, and the steeper you could make this ramp before that block would finally start to slip. Okay, we've handled a single block on a flat surface and on an incline. Now let's really ramp up the complexity. What happens when you have friction between multiple objects, like, say, one block stacked right on top of another? You might think it's just more of the same, but the physics actually changes in a huge way when we go from a simple setup, like the one on the left, to a stacked system like this one on the right. Suddenly, there's a whole new layer of interaction to think about. See, with stacked blocks, you suddenly have multiple surfaces to worry about. You've got friction between the bottom block and the ground, of course, but you also have friction between the two blocks themselves, and each of those surfaces could have a completely different level of grippiness. To solve these kinds of puzzles, you really have to think like a detective. You have to ask a bunch of questions. Are the blocks going to stick together and move as one piece? Or is the force going to be so big that the top block just slips right off the bottom one? The only way to figure it out is to look at each block by itself and analyze all the different forces acting on it. Okay, let's tie all of this together with an amazing real-world example that might just break your brain a little. Let's talk about riding a bicycle. So really, stop and think about it for a second. We tend to think of friction as something that just slows us down, right? And opposing force. So when you're pedaling forward, which way is friction pushing? Is it helping you or is it getting in your way? And the answer is Honestly, it's pretty wild and totally counterintuitive. When you pedal, you're making the rear wheel try to push the ground backward. Well, static friction opposes that motion, so it pushes the wheel and the whole bike forward. That's right, the friction on your back wheel is literally the force that's pushing you forward. Meanwhile, the front wheel is just getting pushed along for the ride, so friction acts backward on it, creating just a tiny bit of drag. All right, so we've been on a pretty quick journey through the invisible world of friction. What are the big ideas? What are the key takeaways you should really walk away with? Okay, let's boil it all down. First, remember friction has two faces, that super strong static grip and the weaker kinetic slide. Second, that static grip is always the stronger of the two. Third, when you're on an incline, friction has to go to battle against gravity. And finally, and maybe the coolest part, is that friction isn't always the bad guy. As we saw with the bicycle, sometimes it's the hero that's actually pushing you forward.
And that leaves us with one final thought. You know, we complain about friction all the time. It wears things out, it makes things harder to move, but the next time you take a step, just think about it. Without that static grip between your shoe and the ground, your foot would just slip backward. You wouldn't go anywhere at all. So yeah, friction can slow us down, but could we even function in a world without it?